honored to be here in NodeTLV, and welcome to my session about the V8 and the changes that were in V8 and how they will boost your server performance. So, at first, I need to talk about myself. Of course, so my name is Tamar. Actually, my big interest in Node started when I founded my own startup a few years ago. And I wrote the entire backend in Node, and from that point, I just started to get really deep into the technology and JavaScript and the ecosystem, etc. I work in Axum Cyber. That's a really cool company. You should really check us out. And, well, the clicker is not working. So, with no further ado, let's start with a V8 deep dive into the ocean. And, well, V8 is a really crucial component in Node.js architecture. Here's the architecture, and here's the V8 engine, and it has really significant part in code parsing and memory management. And let's start with the V8 architecture. So this is the code parsing pipeline. There is a chance that I'm going to take you down the memory lane into compilation courses in the university. You see here abstract syntax tree, AST, and two kinds of compilers and interpreters and bytecode and binaries, and we're going to get into all of that. So how that code parsing pipeline has evolved. What were the changes that makes it so fast? So what's happening when your Node.js server is running? Okay, so let's first talk about the parser and the AST. Okay, so we have our JavaScript code. The JavaScript code is being sent to a parser. The parser is parsing it into tokens, and from that tokens, we are building an AST, an abstract syntax tree. And now let's talk about the ignition interpreter, which is a very important component in that pipeline. The ignition interpreter is an interpreter that takes the output of the AST line by line and parse it into bytecode. And then we have the Turbofan compiler. Here it is. And Turbofan compiler is an optimizing compiler. It takes a code that ran a large n of time, let's say 1,000 times, and create an optimized binary for that code. And from that point that it creates the optimized binary, every time that that code would run, the ignition interpreter is going to fetch the binary and run it instead of parsing into bytecode. And we want to help Turbofan to work fast, because Turbofan is the component that can make our performance really best. So in order to make Turbofan work fast, you need to use fewer input types in your functions. Let's talk about that. So you see here that function is monomorphic, which means that it has one input type. It's not the number of parameters. It's the number of types. And that function is polymorphic. It has two types. And when we're working like that, well, we're happy. Turbofan is happy. It can create the binary very efficiently, do a very efficient memory allocations. So that situation is good. That situation is not really good. That's a megamorphic function with 5 types as an input. So I guess all of you are really scared right now and thinking, oh my God, I'm going to go over the code and make sure I won't have a lot amount of types when I'm writing the code. So I believe that, first of all, there's no need for panic. And second of all, when you're doing segregation and when you're doing good design, you will get to that situation. So you don't need to do it on purpose. But just remember that would make the optimizing compiler work really slow. So now let's talk about another tricky part. What is an optimization and de-optimization? So we're here in that part. Okay, so we said that after a large n, Turbofan is getting a hot code and is generating an optimized binary for that code. In order to do that, it has assumptions. It's assuming something. Let's think that we have a function that is being executed 4,000 times, and that function receives a string as an input. So Turbofan assumes that that function would always receive a string. And that's the assumption. If we're going to call that function with a number, then our assumption breaks. And in that moment, Turbofan is throwing away the binary that it generated. And we're going back to ignition, bytecode, and slow. Okay, so now we are going to see several examples, or actually not several, 2 examples of a de-optimization scenario. Okay, so we have that class person, and that class has 2 properties, a name and an age. And look, we have that function, and that function receives the person. And what's actually that function is doing, it's doing get age. Okay, so we have the person object, and I'm running it in a loop 1,000,000 times. That's like a micro benchmark. I'm taking a problem and isolating it. Well, imagine that in real servers, the function just executed a lot of times, and after a large n, let's say 1,000, a binary is being attached to the function getAge. Okay, so that is the benchmark that we're taking. Okay, so we have this loop. Okay, well, when your server is running, we're executing a function a lot of times. Here, I'm just isolating a problem, and the binary is going to generate for the function getN. And look what's going on here. Well, now I'm creating a person object, and for that person object, I'm going to attach one property, which is a salary, and that is a dynamic property. At that point, what's happening is that the binary which Turbofan has created has been released because the type of this object was changed behind the scenes. That is not good. Why the type was changed? So let's talk a little bit about JavaScript classes, object, and the prototype chain. So as you know, in JavaScript, we don't have types, but what's happening that the object student, actually the prototype of the object student, is pointing to the prototype of the object person, is pointing to the prototype of the object, and behind the scenes we have a hidden class which is created, and the exact wording for that hidden class is a shape. We're gonna explain how shapes are working later on. So the shapes are being created. What's happening here? The shapes are part of Turbofan checks in order to generate the binary. Turbofan checks the shape, the hidden class, in order to understand how many memory it needs to allocate. And at the minute that we have added one property, the shape has changed. Turbofan thinks that we have a different type. We actually have a different type behind the scenes and throws that binary away. Now let's do a small benchmark and let's see it like in action. Again, we have a setup. That's the setup of our benchmark. So we have that function, and that function receives a string. And what it does, it's just concatenating the string, and we're gonna build here, as you see, a very large array of characters and we're gonna check something on that array. Okay, so now we're doing the benchmark twice. First, we're gonna run this function, and that function is gonna receive a string all the time. String, 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 string. Yeah, all is good, 1,000,000 times. Then I'm gonna cause V8 to go crazy a little bit. And as you see, it just chose like a really random index. And I put a number. It doesn't matter, I put an 8, but I can just like put any number in here. And I'm gonna run that loop again. and I have a number in the middle. So that is a de-optimization scenario. The binary of Turbofan is going to be thrown to the garbage. And let's see the test results. You see that when the types were consistent, it took me about 6.5 milliseconds. And when the types are not consistent, it took me 8 milliseconds. It's about 40% more. That's huge. By the way, another comment that I would like to add, that after we're in a de-optimization scenario, let's assume that the first time of the optimization was like 1,000 execution. The next time, until Turbofan would create a binary, would be like 500,000 executions. Like the next time that the binary is going to be created would require us much more executions. So, guys, be consistent with your types. So, actually, a lot of you are writing TypeScript, and you probably think that TypeScript would prevent you from those situations. Well, you're right. It would prevent most of them, but still, I can give examples of like microservices environment. When an input goes from one microservice to another, remember that at the end, you're deploying JavaScript code. And there are situations, especially in runtime, when you're getting types that you didn't expect of. So TypeScript would prevent like a lot of the problem, but not all of it. So just be consistent with your type and validate them everywhere. Let's go back to our V8 architecture. So we spoke a lot about ignition, interpreter, and the Turbofan compiler, and optimization and de-optimization. So the question was, or is, what actually needs improvement? Where were the weak spots of V8? Okay, so what was actually missing is mid-tier optimization. There are several scenarios where V8 had a weak spot. First scenario is application start. And we have command line application, and we have dynamic environments. In dynamic environments, where our code is getting the process of de-optimization multiple times, well, those scenarios were weak. And in those scenarios, you know, when Turbofan doesn't have a lot of time to get warmed up. So, look, we have a new, that's like a change that they did. We have a new component in our pipeline. That component is called a SparkPlug. Okay, so actually SparkPlug is generating machine code for every bytecode that the ignition interpreter is generating. So ignition is generating a bytecode, and immediately, in background, SparkPlug creating a machine code which is non-optimized. Okay, so I wanted to give you a small example to understand what's happened before SparkPlug and after SparkPlug was added. So let's look at our code. We have variable A, and we have do stuff 1 and do stuff 2. So before SparkPlug, everything was like bytecode, and the JVM underneath parsed that bytecode to machine code. And only after like a large N of executions, Turbofan has generated an optimized binary. But after we have added SparkPlug, what's happened is that we have machine code running all the time. We're calling do stuff 1, we have machine code. We're calling do stuff 2, we already have machine code. And yes, the Turbofan, the optimizing compiler, is getting into the picture after like, large N, as we see here. So that is the change. Few things about SparkPlug. Well, just think about it. SparkPlug doesn't have a lot of time to do optimizations. Actually, it gets like bytecode from ignition, and it has to generate machine code very fast. There is an advantage here that ignition has done the hard work, like variable resolution and understanding about the parentheses, whether that is an error function or not. So that was done by ignition, and actually SparkPlug is working in a for loop So every bytecode which is being generated is being sent to SparkPlug, and a machine code is being generated. Now I would like to show you like real-world performance benchmark. We were like taking a problem and isolating it. So this is a server that I have, and it's served like several requests. And you can see that on previous Node versions, where we didn't have the SparkPlug magic, it took that server 1 second to get initialized. But when we are advanced and we have a SparkPlug compiler, we get an improvement. We get 40 milliseconds, which is an improvement of about 40% of the performance. And that has come a lot from the SparkPlug. Okay, now I wanted to take one feature, ES6 modules, and see how they are parsed in our coding pipeline. So CommonJS, I guess all of you know, past, we're working with require, and ES6 modules, I guess all of you are familiar with that as well. We're writing import something from something, and here we have join from path, and we're working with this. That is cool. Why working with ES6 syntax would make your Node.js server works much faster? Why is that? So, first of all, loading a CommonJS module is what's called dynamic loading, and that is a synchronous operation. I hope that everybody here knows that when you're doing a synchronous operation, your event loop is being blocked, and your server freezes. So when you're doing that activity, when you're executing require, actually your server freezes and waits. And you get spikes on runtime. And it harms your performance. Not really nice. If we're looking at our pipeline that we have discussed a lot, so when we have a require, it's only being fetched in the ignition. And at that point, well, path model is huge, right? It has like tons of functions, tons of variables. I only need join. What's happening here because of the dynamic loading and runtime? Because it's done by ignition, I'm going to get the entire path module into my memory. Why? I don't need it. I need only join and the variables which are connected to join. I don't need everything. And if I'm working with the ES6 module, first of all, this is an asynchronous operation. And second, it is done in the parsing phase. The parser is doing that. And because the parser is doing that, and there is static on analysis here, the parser can understand that I need only the join function and fetch only join and the variables which are related to it, which is important. So work with ES6 modules in many code parts that you can. Now let's talk TypeScript, because I guess that a lot of you work with TypeScript, right? And I was showing like a lot of vanilla JavaScript right now, and you were wondering, yay, I'm working with TypeScript. I mean, I write, import something from something all the time. How is it related to me? I mean, I'm okay. I'm covered. Okay, so just remember that when you are writing TypeScript, you're not deploying TypeScript. You are deploying JavaScript. JavaScript is running at the end, and a JavaScript code that the TypeScript compiler is generating is being served into the Node.js engine. I would like to show you a small property in your TS config, which called module. And if that property has a CommonJS value, then the JavaScript code that's being generated has requires, and you won't enjoy that optimization. That's only an example. You know, I just chose ES 2020. I think that every ES value would work, but pay attention to that property in order to get that optimization in your code. Wow, I have to say that I'm okay with the times Although the logistic problems that we had, I think I deserve some clapping. Woo! We're gonna finish in time. That's unbelievable. All right, so now let's go to class initialization. I said one phrase about shapes. Now the shapes are gonna go back into the picture. Let's talk shapes a little bit. So, in order to understand what V8 did to drastically improve class initialization, we have to understand how JavaScript objects are built behind the scenes. Okay, so how they're built behind the scenes. Once upon a time, before shapes, I had a JavaScript object, and it has two properties, X and Z. And in the memory itself, we had the name of the properties, X and Z. Each one of them was pointing to a set of characteristics. One of the characteristics was a value. Value of X is 1, as you can see, and other characteristics as writable, enumerable, and configurable. I'm not gonna get really deep into them right now. But just imagine millions of objects built the same, and each one of them has property, and that property is pointing to those 4 characteristics, and that is duplicated millions of times. That's just such a waste because we don't need that. And then what V8 did is to do a shape. That is actually the hidden class that the Turbofan compiler is looking at when it's doing optimizations and the optimizations. So what's happening when we have the shapes? We have an object, and in that object, we have the values. We have we have the value of 1, and we have the value of 2, and that object is pointing to a shape. So the change here that the property names are on the shape, and there is a point to those characteristics, but instead of the value, we have the offset. You see? So if I want to fetch the value of X, what I'm doing is I'm going to the memory allocation, going to the shape, understand that I need X, go to the offset. I see that this is offset 0. Go to offset 0 and fetch the value. The value is 1. That lookup of shapes, that lookup of the offset was very expensive because every time we need to see what is the offset and fetch it, and that lookup has harmed the performance very much. So there is a solution for that. Inline caching, the inline cache. Well, the inline cache is a cache for a function. So you see that getX receives X, and then when we're doing O.X, when we're fetching X, what we're doing, we're fetching the object from the inline caching. So this is what we're doing. But that optimization was not present in V8 on class properties until latest versions. So V8 added this improvement. They added inline caching into private and public properties of classes only recently. Okay, so I would like us to do the last benchmark of the day to see how that improved function calls and property access. Let's see the benchmark setup. Okay, this is our beloved class person with a small change because now age is a public property, and we have set age, and we're setting the age with the new age. Yay! And well, what's going on here is now the benchmark is starting or not starting. This is still the setup. We have the get age, and that's the function that we're gonna measure. Get age is accessing age. And we are going to have an array, again, large N, to make Turbofan, inline caching, everything start working. Okay, so we're gonna create like 1 million objects, and we're gonna set the age on all of them. And now that's the benchmark. So we're gonna do get age million times. Again, we're isolating a problem. In real world scenarios, you would have like a server, that function is gonna be called multiple times, but that's like a micro benchmark isolated. So now you can see that when we are in old Node.js versions, which receive old V8 versions, that loop is taking 3.2 milliseconds. And when we were advanced to version 19, that loops take 2.7 milliseconds. And that is also like, I think, 30% improvements because of this class initialization and V8 improvements. So, everybody, I hope you enjoyed it. And I hope you learned something. And I hope you had like nice insights about V8. And that's me.